So the last thing we're going to look at is going back to this idea of rates of change. So first of all, let's recap the idea. Remember, calculus measures the rate of change. But then sometimes to solve the problem, we need to find more than just one rate and combine them together. And that's where we use, well, call it whatever you like. Chain rule, implicit differentiation, rates of change. I mean, it's all the same idea. You could think of them like fractions, I guess, and the dx's cancel and you get divided too. Let's look at this example. We've got a block of ice in the form of a cube. Has one edge 10 centimetres long. Hence all the edges are, of course, because it's a cube. It's melting so that its dimensions decrease at a rate of 1 millimetre per second. We want to know the rate the volume is decreasing when the edge gets to 5 centimetres. So how do we approach a question like this? Well, I guess the first thing is, what rate are we trying to find? There's my cube. We know a side is x. So it's dv to t that we want to find. Now we trawl through the question to look for some information they've given me, and they have given me a rate. They've said the edge, which I've called x, is changing at a rate of 1 millimetre. Negative because it's decreasing. And I've changed it to centimetres, you'll notice, because they've told me the edge is 10 centimetres and they want to know the answer when the edge is 5 centimetres. So it makes more sense to put the rate in centimetres per second rather than millimetres per second. Okay, we want dv to t, we've got dx to t, so ideally what I'd now like to work out is dv dx, and then I can link it all together. Fortunately, we have a formula for the volume of a cube, x cubed, hence the name. Cube. Differentiate that with respect to x and we get 3x squared. We can now create the rate. Substituting 3x squared for dx to t times minus 1/10. There's my formula. We want to know when the edge is 5 centimetres long. So it's a substitution question now. When x equals 5, we end up with minus 7.5, like that. I mean, that's just you working out to solve the problem. It's a word problem. You answer the question you're being asked. So how have I've concluded this way. So the volume is decreasing at 7.5 centimetres cubed per second. I suppose you could say the rate of change of the volume is negative 7.5. I mean, you could say that. But basically, solve the problem. Let's try this one. A vessel is in the form of an inverted cone. Vertical angle 90 degrees. If the depth of the water in the vessel is x centimetres, find the volume of the water. I always like diagrams so I can see what I'm talking about. Inverted cone. It just means a cone that's sort of upside down to what we traditionally think of as a cone. More like, I guess, an ice cream cone. They've said the vertical angle. Well, the vertical angle is the angle at the apex of the cone. That's 90 degrees. There's some water in there. I've just put a blue circle in there to represent where the water is. We're told the depth is x. We want the volume there. Okay. The nice thing about that being 90 degrees is I can create a right angle triangle there. But because my cone is symmetric, I know that that angle has to be 45. So to find the radius, well, I've got an isosceles triangle, haven't I? So therefore it's got to be x as well. Let's find the volume then. 1/3 pi r squared h for a cone. So in our case, x squared times x, 1/3 pi x cubed. So there's the first part of the question. Water is being poured in at a rate of 0.2 centimetres cubed per minute. Find the rate the depth is increasing when the water depth is 4 centimetres. We want to find dx to t. How is that depth changing? They've given us that dv to t is 0.2. Well, I've made it a fraction, 1/5. So ideally now we want dv dx. Well, actually dx to v, but that's not a problem. I can just turn dv dx upside down and we'll get that. Hence why we did part A. We have a formula. Volume is 1/3 pi x cubed. So dv dx then is pi x squared. Sub it in and we have our formula. But dx to t, how is it changing? How's the height? Well, it's inversely proportional. That kind of makes sense. Think about pouring water into a shape like that. It would start really quick because it's so narrow to start off with. But as it gets wider, well, yeah, sure, that height is going to go up slower and slower and slower. So that's basically what that's saying. All right, let's use it. We want to find when x is 4. I'll leave it as an exact answer. So 1 over 80 pi. The depth is increasing at 1 over 80 pi centimetres per minute. A spherical bubble is expanding so that its volume increases at a constant rate. Or another way you could think about it is you're blowing air into a balloon, but you're doing it at a constant rate. So you just sort of go and not changing the rate you're blowing air into it. But how would the surface area change? And again, maybe it's easier to think about the balloon rather than the bubble. What's happening to the surface area? The rate of change of that. We want to know when the radius gets to 10 millimetres. Is this going to be directly proportional or inversely proportional, do you think? Inversely. Because think about it, you first blow air in and it expands really quickly. But remember, if you have ever done this, you get to a balloon and it's getting really big and someone goes, and it only expands a little bit now, but everyone's going, oh, it's going to pop. Put a bit more in and just a little bit. So as that radius gets bigger, it comes up smaller. We want the rate of change of the surface area. I'll just call S for surface area. So ds to t is what we're trying to find. We've been given dv to t. I'm going to use 3 rates now for this one. Because ds to t, I know dv dt. I can work out ds dr because I can get a formula relating surface area and radius. And I can get a formula for dv dr because I've got a formula volume and radius. See, but to get dv ds, which is what I'd need here to get cancelling happening, I don't have a formula that links volume and surface area together. So I need a few rates here to get to what I'm looking for. Okay, volume. So dv dr is 4 pi r squared, which is the one that always fascinates me, because of course that is surface area. Differentiate volume, you get surface area. And there's surface area, and ds dr becomes 8 pi r. So sub all that information in, and there it is, inversely proportional, 140 on r. So as r gets bigger, the surface area change gets smaller and smaller. We want when the radius is equal to 10, so dv to t is 14 for this one. Answer the question. When the radius is 10, the surface area is increasing at a rate of 14 millimetres squared per second. But the other thing to point out here is make sure you read the question and know exactly what they're asking for. Because sometimes they might say, what is the area when the surface area is... So they might actually want you to work out that surface area and things like that. Make sure you know what the question is that you're answering, because let's face it, once you've got your formulas here, the actual solving the problem is not hard, it's just the substituting numbers in. So make sure you're substituting into the right thing. Okay, 16A, we'll have a look at some rates of change questions.